floating point types. So in this video, we're going to continue on, and we're going to start off with the cascading the insertion operator. Now note that there's only one cout statement in with1 and with2 programs that we looked at in the last video. Although it's written on multiple lines, I'm doing this so that way we take advantage of the fact that the compiler ignores white space and that the insertion operator can be cascaded. The effect is the same as using 4 separate statements, each beginning with cout. Now, multiple definitions. We initialize the variables pop1, pop2, and pop3 to specific values at the same time we define them. This is similar to the way we initialize character variables in the character variables example. However, here we've defined and initialized all 3 variables on one line using the same long keyword and separating the variable names with commas, as you can see here. This saves space where a number of variables are all the same. Another way we could have did this was we could have said long pop1 equals 2425785, and then we could have said long pop2 equals 47, and then we could have said long pop3 equals 9761. But we used one long to accomplish the same thing. So the IO manip header file, the declaration for the manipulators except end line are not in the usual IO stream header file, but in a separate header file called IO manip. When you use these manipulators, you use the include this header file in your program, as we do in the with2 example. As you can see here, we had to include IO manip in order to be able to use the setW operator. The setW manipulator. Variable type summary. Our program examples so far have used 4 data types: int, character, float, and long. In addition, we've mentioned types bool, short, double, and long double. Now let's pause now to summarize these data types. Table 2.2 shows the keyword used to define the type. The numerical range in the type can accommodate the digits of precision in the case of floating point numbers, and the bytes of memory occupied in a 32-bit environment. Unassigned data types. By eliminating the sign of the character and integer types, you can change their range to start at 0 and include only positive numbers. This allows them to represent numbers twice as big as the sign type. As we can see here in the unassigned versions, so if we were to do unassigned character, we would have a numerical range low of 0 with a high of 255. Bytes in memory would be 1. If we did an unassigned short, it would be 0, and we'd have a high of 65535. Bytes of memory consumed would be 2. If we did an unassigned int, we'd have a numerical range low of 0, and as you can see here, 4,294,967,295 with bytes of memory at 4, and a similar case here for unassigned long here at the bottom. Unassigned types are used when the quantities are always positive, such as when representing a count of something, or when the positive range of the sign types is not quite large enough. To change an integer type to an unassigned type, precede the data type keyword with the keyword unassigned. For example, an unassigned variable of type character would be defined as unassigned character variable. Exceeding the range of signed types can lead to obscure program bugs. In certain, probably rare situations, such bugs can be eliminated by using unassigned types. For example, the following program stores the constant 1.5 billion, both as an int in signed variable and as an unassigned int in unsigned variable. So let's take a look at it. 1.5 billion, yes. Let's take a look at it. So this is going to be tests, signed and unsigned integers. And in our int main, we're going to start off with an integer signed variable. We're going to set that equal to 1.5 billion. So 1, 1, 2, 3, 1, 2, 3. And then we're going to do an unsigned int, unsigned variable. We're going to set that equal to 1 billion. And then we're going to do a signed variable. We're going to set that equal to the assigned variable times 2. And then our unsigned variable, that's going to be equal to unsigned. Oops. That's going to be equal to unsigned variable times 2 divided by 3. And this is going to be the calculation exceeds range. And this is going to be the calculation that's within range. So now if we print it out on the screen, we'll just do a cout. This will be the signed variable. We'll set that equal to, and then we'll pass in the signed variable. And then we'll just end line. This is going to be wrong. All right. And then we'll do a cout of the unsigned variable with that equal to it, and then we'll pass in our unsigned variable, and then we'll just do our end line. And this is it with it being okay. We'll keep our return 0 at the bottom, and I'll go ahead and I'll build and run this. And we can see our signed variable here at the top with what it's equal to. And I think I might be missing some zeros here, right? 1, 2, 3, 1, 2, 3, 0, 0. We're missing a few zeros in here. So if we add those and then run it again, then it should give us what we're looking for. Yeah, see that? So what's wrong here is because our calculation exceeded our range in our signed variable, we see a negative 431655765. Now for our unsigned, since it's within range, we see 1 billion here. So the program multiplies both variables by 2 and then divides them by 3. Although the result is smaller than the original number, the intermediate calculation is larger than the original number. This is a common situation, but it can lead to trouble. In Citus, we expect that 2/3 the original value, or 1 billion, will be stored to both variables. Unfortunately, in signed variable, the multiplication created a resulted 3 billion that exceeded the range of the integer variable. And this was the output here, as you can see. It was negative when it shouldn't have been. The signed variable now displays an incorrect answer, while the unassigned variable, which is large enough to hold the intermediate result of the multiplication, records the result correctly. So our calculation that was done here, the signed variable threw the calculation out of range, and then our unassigned here kept it in range. So when we're programming and we want to do calculations, if we know that the signed here is going to exceed the range of what we're calculating, then we need to make sure we use an unassigned, so that way we remain accurate. So the moral is this: be careful that all values generated in your program are within the range of the variables that can hold them. The results will be different on 16-bit or 16-bit computers, which use different numbers of bytes for type int. Type conversion. C++, like C, is more forgiving than some languages in the way it treats expressions involving several data types. As an example, consider the mixed program here. This will show mixed expressions. So if we have an integer count equals 7, and then we have a float of average weight, and we set that equal to 155.5 Fahrenheit. I'm sorry, float, to specify that it's a float. That's not Fahrenheit. But now we'll do a double. Total weight equals count times average weight. Then we can print that out on the screen. Total weight equals, and then we'll just pass in total weight, right? sure you guys are familiar with this by now. What we're doing is we initiated our integer count, set that equal to 7, and then average weight equal to 155.5, and then double is total weight, and then we set that equal to count times the average weight, and then we just took double and printed it out on the screen. So here's a variable of the type integers multiplied by a variable of type float to yield a result of type double. This program compiles without error. The compiler considers it normal that you want to multiply or perform any other arithmetic operation on numbers of different types. Not all languages are this relaxed, though. Some don't permit mixed expressions and would flag the line that performs the arithmetic and mixed as an error. Such languages assume that when you mix types, you're making a mistake, and they try to save you from yourself. C++ and C, however, assume that you must have a good reason for doing what you're doing, and they help carry out your intentions. This is only one reason for the popularity of C++ and C. They give you more freedom, of course. More freedom, there's also more opportunity for you to make a mistake. Now, automatic conversions. Let's consider what happens when the compiler confronts such mixed type expressions as the one in mixed. Types are considered higher or lower based roughly on the order shown. Order of data types: long double, double float, long int, short character. Order from highest, as you can see here, and then the lowest. The arithmetic operators such as plus and multiplication like to operate on two operands of the same type. When two operands of different types are encountered in the same expression, the lower type variable is converted to the type of the higher type variable. Thus, in mix, the integer value of count is converted to type float and stored in a temporary variable before being multiplied by the float variable average weight. The result, still of type float, is then converted to double. So then it can be assigned to double variable total weight. These conversions take place invisibly, and ordinarily you don't need to think too much about them. C++ automatically does what you want. However, sometimes the compiler isn't so happy about conversions, as we'll see in a moment. Also, when we start to use objects, we will in effect be defining our own data types. We may want to use these new data types in mixed expressions, just as we normal variables in mixed expressions. When this is the case, we must be careful to create our own conversion routines to change objects of one type into objects of another. The compiler won't do it for us, as it does here with the built-in data types. All right, so we're just going to end video here. If you're watching, you should have learned a little bit about unassigned variables. So in our next video, we're going to continue on talking about casts. So if you're interested in our next video, head on over to database-tutorials.com. Check out our YouTube channel here. And until next time.